Something that you have to be good at doing is reading what are called potential energy diagrams. So I'm going to go through that in this lesson with you guys today and just give you some information that you need to be able to do that effectively. So the first thing is that I'm going to point out is that we've got two reactions here. This is the decomposition of ammonia and this is the formation of ammonia. You can see that this is an endothermic reaction because I've got the energy term on the reactant side. You can see that then obviously the reverse part of that reaction, or the reaction written in reverse, is going to be then the formation, which would make it exothermic, and so the energy term is over here on the product side. A couple of things that you need to know about these potential energy diagrams and how they're set up. First of all, on the y-axis we have potential energy. So the higher I am on this side, the more potential energy I'm going to have. And on the x-axis we have what's called the reaction coordinate. Really, this is just kind of a fancy way of saying time. So just as the reaction progresses, we see these changes in potential energy, which makes sense because a chemical reaction, we know, as we've established, is a change in potential energy. And so that change really just happens from our start point and our end point. So in an endothermic reaction, you can see that our reactants have much less energy than the products. And in an exothermic reaction, our reactants have more energy than the products. And what makes an endothermic reaction endothermic is that it has a net gain of energy. And for an exothermic reaction, it has a net loss of energy. Now, I say net gain or net loss because in both reactions will undergo a step where they absorb energy, and they'll undergo a step where they release energy. But one reaction will absorb a whole bunch and release a little bit, and the other reaction will absorb a little bit and release a whole bunch. And so there's this net either gain or loss of energy when that happens. So the example I like to give for that is if you were to go to the bank and put in $1,000 and then go to the store and spend $100, you're going to have a net gain of money. Your bank account's going to be in the positive. But if you go to the bank and put in $100 and go to the store and spend $1,000, then your bank account's going to be in the negative. And so that's what happens with these chemical reactions here. An endothermic reaction in this absorption step absorbs a lot of energy. And so from the reactants to the top of this little bump on the graph, this is what's called the activation energy. It's how much energy is needed in order to break the bonds of the reactants. And that also is true for an exothermic reaction, but you can see that the activation energy is much smaller. And so not as much energy needs to be absorbed by that reaction in order to make it go. So a good example of this would be, for example, if we're in the lab and we're trying to light a Bunsen burner, the Bunsen burner doesn't light itself. You have to use a striker, some sparks, to get that reaction to begin going. And so that's the activation energy. It's a very small one, but it is an activation energy where energy does need to go into the reaction to make it go. Over here on this side, you can see that on this side of the bump on the graph, we have a dip in potential energy. And what that means is that we've got a certain amount of energy that has been released when we form the products. And so we've got this concept of that energy in, or energy is required in order to break the bonds of the reactants, and energy is released when we form the bonds of the products. Same thing happens here. Energy goes in to break the bonds of the reactants, and then energy is released to make the bonds, to make the bonds of the products. So where we get these delta H values, these enthalpy changes, is the difference between where we started with the reactants and where we ended with the products. And that is our delta H. Sometimes a common mistake I see that some kids make is they'll say that the delta H is from the top of this bump down to the reactants, or sometimes they'll just say that it's this little spot right here. And so you have to be careful with that. The delta H is the difference between where the energy of the reactants is and the energy of the products are. And so for an endothermic reaction, you can see that we had a net gain of energy And so my delta H needs to be positive to indicate that it's an endothermic reaction, and how many kilojoules. In this case, it's 91.8 kilojoules. For this reaction, again, the same thing is true. You can see the delta H is the difference between the reactants and the products, but in this case, now we've got a net loss of energy, and so my delta H must be negative. So for an endothermic reaction, delta H's are positive. An exothermic reaction, delta H's are negative. That's no different from some of the other lessons that we've gone through. And really all you got to be able to do is identify what is an endothermic and what is an exothermic reaction. You need to be able to, on these graphs, identify what is the activation energy and also what is the delta H, and correctly identify that endothermic potential energy diagrams have a positive delta H and exothermic is a negative delta H. And that's what I got for you guys on this one. Thanks for watching.